Hi everyone. Today we will discuss on the topic factors affecting magnitude of 10 dq or factors affecting magnitude of crystal field stabilization energy. The factors are mainly nature of the ligand, oxidation state of the ligand, size of the d orbitals, geometry of the complex, and last one is Z effective nuclear charge on central metal atom. So, here we will discuss the factors one by one. First one will be nature of ligand. The ligand with large negative charge and small size produce large crystal field splitting. The strength of a ligand is in the following order. Here you can see there are two examples. FeH2O 6 times, the charge will be plus 3, and FeCN 6 times and the charge is minus 3. Here H2O is a weak field ligand. This we can see by the spectrochemical series. H2O is a weak field ligand whereas Cn is a strong field ligand. Here is the electronic configuration of iron, that is 3d6 4s2. Whereas the charge is plus 3, then it will become 5. We have to calculate the magnetic momentum will be 5 into root of 5 into 5 plus 2. It will become 5.92 Bohr magneton. Bm is nothing but Bohr magneton. This will be high spin complex. This value comes for high spin complexes. Next, coming to the next example, FeCN 6 times as I have said, then mu value will be 1. If we calculate the Bohr magneton, then it will become 1.7258 Bohr magneton. This will become low spin complex. If the value is high, then it is high spin complex. If the value is low, then it is low spin complex. Next, moving on to the second factor, that is oxidation state of the metal. Oxidation state of the metal, in this the crystal field splitting increases with increase in the oxidation state of the metal. As the crystal field splitting increases, even the oxidation state of the metal should also be increases. This one is directly proportional. Oxidation state of the metal is directly proportional to the crystal field splitting energy. Okay, here we can take two examples. Here Cn is always strong field ligand. As I have said, here Cn is a strong field ligand. Here both examples carry Cn, that is strong field ligands, but we have to see the oxidation state of the metal. Here the oxidation state is -4, here it is -3. As -3 is greater, the oxidation state on the metal is greater. So FeCN 6 4 minus 4 is always smaller, whereas FeCN 6 minus 3 is greater. Next, moving on to the third factor, that is size of d orbital. For similar complexes, crystal field splitting increases with increase in the size of a d orbital. This one is also directly proportional to the crystal field stabilization energy. Next, moving on to the fourth factor, that is geometry of the complexes. This depends on the geometry of the complex, how the complex is formed. CFSE, crystal field stabilization energy in case of octahedral is nearly double to that the value of the tetrahedral complex. That is, octahedral is mostly probably equals to 4 divided by 9 times of tetrahedral complex. This is due to the less number of ligands in the tetrahedral complex. Here you can observe this is octahedral complex, this is tetrahedral complex. In tetrahedral complex there are only 4 ligands, whereas in the octahedral complex you can observe 5 ligands, 5 to 6 ligands, whereas always the octahedral contains more number of ligands compared to tetrahedral. So octahedral will be it has the more value compared to tetrahedral. That is that this geometry explains the crystal field stabilization energy, that is octahedral always has the more splitting energy. Then there is a last factor, that is Z effective nuclear charge on central metal atom. The Z effective nuclear charge is more, then the CFSE will be more. As the above factor says, this also is directly proportional to crystal field stabilization energy. Z effective increases due to the shielding effect. The Z effective nuclear charge always increases due to the shielding effect present in between the electrons. Here we can see by taking the example of 3D elements. 3D elements are greater than 4D, then greater than 5D. Here is the SPDF shells. As the atomic size goes on increases, the size goes on decreases. When repulsion occur between the D and F moves away and the Z effective nuclear charge increases. As the repulsion occur between D and F orbital moves away, and then the Z effective nuclear charge occurs on the D orbitals. This is what Z effective nuclear charge wants us to get the explanation. This was about the factors. I hope you understood. Thank you for watching the video.